Hello there. In this lesson, we're going to finish up our thermodynamics unit by looking at reactions that are spontaneous. So a couple things in these pictures that are spontaneous. One is my daughter falling to the ground here. This is an occurrence that happens and therefore is spontaneous. Things that don't happen are her jumping off of here and flying up into the air. That would be non-spontaneous. Here we have a chemical system doing the same sort of thing. We have alcohol in this little dish that my son is giving a little spin. It's making that kind of cool tornado flame. And that reaction is spontaneous because it's happening, right? You have ethanol and oxygen, and you got CO2 and water coming off of that. And since it's happening, that means it's spontaneous. So here we are in words. If a change occurs under a specific set of conditions, that's called spontaneous. If it does not occur, that is considered non-spontaneous. Another good example here is diffusion. Diffusion that is spontaneous would be going this way, right? This would be spontaneous. You open this valve, the gas will move that way until it's all evenly spread throughout the two chambers. What would not be spontaneous is the reverse. If you had a bunch of these particles that all suddenly decided to randomly go that way and pack themselves into one end, that would be non-spontaneous. Now, entropy is related to spontaneity because if there is an increase in entropy, that tends to be spontaneous. So this is a positive delta S, usually spontaneous. Right? Over here we have this nice ordered solid, and over here we have this mixture where the particles are mixing all together. Maybe this is a liquid that's dissolving it. Could think of it like some salt on some ice, and eventually getting this nice mixture. The mixing and the particles being spread apart from each other, this is more likely to happen and therefore spontaneous. The opposite direction, where there's a negative delta S, tends to be non-spont. My writing's terrible today, sorry. So through a whole bunch of observations and years of study and making measurements about the world around us, scientists have concluded and even enshrined in a law, the second law of thermodynamics, and that entropy changes in the universe must always be positive. So that means that even if you have a system that's negative, there has to be a corresponding much greater change in entropy, increase in entropy in the surroundings, so that the overall entropy of the universe is always increasing with every change. And of course, if the system is already an increase in entropy, well, as long as the surroundings don't increase or don't decrease more than the increase of the system, then you're still okay, and you will still end up with an increase in entropy overall. So always increasing in entropy, that is the second law. As a equation, you can say that the total entropy is always going to be positive, and so the total entropy equals the system plus the surroundings, and always has to be greater than 0. Now, measuring the entropy change of the surroundings is a tricky thing because it's the whole rest of the universe, but what we can do is relate it to the enthalpy change of the system. Now, the enthalpy change of the system is how much energy is being either absorbed or released into the surroundings. And we know that if you heat up the surroundings, you're going to increase the entropy, right? If we have heat coming out here, it's going to increase the entropy of the surroundings. And conversely, if you are withdrawing heat from the surroundings, that's going to decrease the entropy of the system, right? That's going to be a negative delta S of the system. So that means that instead of worrying about trying to measure the entropy change of the surroundings, we can relate it to the enthalpy change of the system divided by the temperature. That gives you a nice value that you can use. So here's a tricky little bit of equation manipulation that we're not going to have to do in class, but I just want you to be kind of aware of it. Instead of using the entropy change of the surroundings as we originally had, system plus surroundings equals the total of the universe, and it always has to be increasing. That's the second law, right? We can use the change in enthalpy of the system and sub that in for the entropy of the surroundings. So when you do that, you end up with this thing here. So you've got it both in terms of the system. So that's good because we can measure both of those things. We calculated both of those in earlier lessons. And then they do a little rearrangement here in order to make it a little more manageable and enable us to determine whether or not we'll have a spontaneous reaction by calculation. So that rearranged equation is now simplified in order to be useful to us. And the term on the left-hand side here is called Gibbs free energy. It's given the symbol delta G. And so this is what's going to tell us whether or not a reaction is spontaneous. If that delta G is less than 0, if it's negative, then you're going to have a spontaneous change or spontaneous chemical reaction. And conversely, if it's positive value, then it's not going to be spontaneous. It's not going to happen. Stuff's just going to sit there in the beaker. Okay, so now there's 4 different possibilities. Delta H can be positive, delta H can be negative, delta S can be positive, delta S can be negative. So let's have a look at what's likely to happen in these situations. The first one here we're going to look at is when delta H is positive and delta S is also positive. So delta G is going to equal a positive value minus whatever the temperature is times a positive value. So we take a positive and subtract another positive. This will be negative only if this is big, right? Only spontaneous if big, right? So big depends on this temperature, therefore high temperatures. At low temperatures, it's not going to be spontaneous, but at high temperatures, it'll make this value large enough so that you'll have a negative for your delta G. All right, let's look at box number 2 here. Delta G equals, in this case, we keep in delta H positive minus T, and this time delta S is a negative value. So if we got positive here and then we're subtracting a negative, that's making it more positive. So this is always going to be positive. Therefore, never spontaneous. And there's a bunch of reactions like that. It doesn't matter what you do, they're never gonna happen. Okay, delta G equals this time negative delta H minus T and a positive delta S. So we got a negative value here, and then we're subtracting a positive. And so that's just going to make it more negative. So this is going to always be negative, and therefore always spontaneous. Doesn't matter what the temperature is. Finally, let's look at negative delta H and negative delta S. So delta G equals negative delta H minus T times negative delta S. So negative already, and then we're subtracting a negative, so then we're making it positive. So as long as this stays small, then the delta G will still be negative. So it'll be negative at low temperatures, or spontaneous at low temperatures, right? And at higher temperatures, of course, this will get too large and overwhelm the negative for the enthalpy, and then you'll end up with a non-spontaneous reaction. All right, there you go, 4 options, and you'll have to use actual temperature values to figure out where you are for some of them. So finally, let's use our Gibbs free energy equation to make a prediction about reaction with some measurements we have here. So we have an enthalpy change here. We got positive 98.8 kilojoules. Great. And we have a temperature, 25 Celsius. Of course, we have to put that in Kelvin. This is 298 Kelvin. And then we're going to multiply that by delta S, which is 141.5 joules per Kelvin. Now, this is kilojoules, and that's joules. So we're going to change this into kilojoules just to match things. So 0.1415 kilojoules per unit Kelvin. Great, so the kelvins will cancel out, and that should give us a kilojoule answer here. All right, so 98.8 minus bracket 298 times 0.1415 bracket equals. And there we go. We got positive 56.6 kilojoules. Therefore, not spontaneous. So the logical follow-up here is, at what temperature would the spontaneity change? When would it become spontaneous? And so you can work that out as well with the same Gibbs free energy equation. All you need to do is set delta G to 0, because that's the point at which it changes from being spontaneous to non-spontaneous, or vice versa, right? So 0 equals, and we've got delta H here, 98.8 kilojoules. The temperature, that's what we want to know, and delta S is 0.1415 kilojoules per Kelvin. Great, so what you do is you isolate T, so you want to have T equaling 98.8 kilojoules divided by 0.1415 kilojoules per Kelvin, and you'll see the kilojoules cancel out. You're left with the Kelvin. So let's get it at 98.8 divided by 0.1415 equals 698 Kelvin. And to change that into Celsius, of course, we'll subtract 273 equals 425 degrees Celsius. So you got to heat this one up pretty high to get this reaction to happen. And that's why if you go to those smelters down in Hamilton where they are converting iron ore into steel and other things, it's super hot, and you'll see those big smokestacks down there while they're burning all sorts of fossil fuels to make that happen. Okay, take care. Talk to you soon.